is Thomas Baruda. I hope that I pronounced that correctly. So he's coming to us from the Northwestern University, and he's going to tell us a little bit about online learning and physical systems. So cool. Whenever you're ready.
All right. Yeah, so hi everyone, I'm Thomas. I'm with the Interactive and Emergent Autonomy Laboratory of Dr. Todd Murphy at Northwestern. And this is my first SIAM conference, and I'm very excited to be here, hopefully not the last. And I think my talk, you'll note, is going to be sort of qualitatively distinct from the rest of the stuff that you've seen here. I like to kind of focus on the bigger picture here of learning in physical systems. And here, I seem to be suggesting that machine learning in physical, like realized material dynamical systems tends to be something different than machine learning at large. And I guess we might ask why. And I think that the question of why sort of hinges crucially on the next question here. Where is the data? So generally, when we're talking about machine learning, we can broadly imagine a optimization process where we have a bunch of parameters that we're going to try to resolve from data-driven observations. And very often we tend to take the availability of this data for granted, not just its availability, but its abundance. And then beyond that, how clean it is and how easy it is, how, just as the previous presentation covered, how noisy it is also matters as well. But in general, when we're doing physical learning, and I'm a roboticist, so I'm thinking of robots here when we're talking about physical learning. Sometimes the data can just be out there in the wild. I love this picture here from a science robotics paper from ETH Zurich. So the sort of data collection process becomes a much more crucial element of your learning pipeline, because now the robot at every single moment in time needs to make a decision about what data to go out there and collect. And this isn't just a sort of aesthetic difference. This actually causes a very formal, fundamental difference in the learning process. It's no longer a passive optimization, but instead it becomes a sort of decision theoretic process, which is, as many of you may know, a different kind of problem structure. So hopefully that motivates the why it is that we should be thinking about physical learning as something different. But now I'd like to think about how. How is it different? And so here I'm going to go over a couple different ways in which physical systems have to learn differently or have to have different unique considerations from non-physical systems. And the first one that I'd like to get going with is the observation that, well, robots break. And if you've ever experimented at all with any robot or any physical system, they don't just break, they break often, and you can always count on them to break. And then even if they don't break, they often experience some sort of irreversible change that may affect their functionality, and we would still like to adapt to. So if I took this humanoid robot and I chopped off its leg, we would still like it to work. And so perhaps we would want some sort of learning system that adapts to this sort of morphological change in the agent. And then, not just catastrophic events matter here. In soft robotics, we design our agents so that they experience fundamental changes to their morphology. And so we should be thinking about this, thinking about how should we build learning pipelines that adapt to these kind of fundamental changes in our in the morphology of our robots. And then, even if our agents aren't the ones suffering the damages, they can still impart changes on their environments. And crucially, people are often a part of these environments, and we really would like people to be protected in this case. So safety is a sort of non-negotiable property of physical learning. We always have to be thinking about safety. What else? Another sort of basic observation is that physical agents are not omniscient. Their perception is typically limited in some way. Just as you and I can't look around corners, a robot with an RGB sensor is not going to be very good at telling depth unless you equip it with an additional sensor or use some very fancy machine learning. And so what this means is that they must be capable of learning under partial information, and their sensory modalities tend to be spatially localized, and this is sort of distinct from how we typically think of, say, control learning problems in reinforcement learning, where often we give the agent a snapshot of the environment, and we get to sort of see how everything evolves in time. This is certainly the case in the type of game based, like video game based reinforcement learning that we see in many fancy applications. And so to fully characterize an object or a learning task, we may actually require to use a schedule of observations, a time series, or a trajectory of observations in time. And we're going to need to be thinking cleverly about how it is that we're going to schedule each action that we take to collect new data and then resolve some sort of learning problem. So the takeaway here is that physical systems have to deal with local measurement models, and we have to have our learning pipelines be robust to this. What else? Perhaps another obvious one is that our physical agents are localized in time. And so we can't just have them do things that work for infinity, right? Like we can't always be relying on asymptotic behaviors in order to learn something. And so ideally, physical experimental learners need to be finding solutions in finite time with few examples, and ideally in real time. And importantly, this can also plug back into safety. So here, for example, I have a figure of a quad rotor vehicle, which we've equipped with a nominal model of its dynamics and a stabilizing controller that keeps it in place. And then what we do is we cause a malfunction in one of its rotors, and all of a sudden it doesn't work. And then naturally, this leads to an instability, and the quad rotor starts to fall dramatically. And so it's clear already that this could be very unsafe behavior. And so the robot needs to be adapting in real time to what just happened. And so this already limits the type of models that we should be considering. Like, for example, a neural network would not be necessarily great for this type of approach because it would not converge quickly enough to keep everything safe. But not just that. The way that we choose our actions may have an impact over the quality of observations that we take and how fast we are able to resolve a usable model. So that's precisely the distinction that I have here. When we choose our actions actively to sort of maximize information about our model parameters, we are able to stabilize the quadcopter really quickly. Whereas when we don't do that and we're just sort of free falling and passively observing the quad rotor's movement, it falls a lot further. Which, of course, could be very critical to safety. Additionally, we can't just infinitely redeploy agents over and over again in the field as we do in simulation. Robot deployment is a very time-consuming and resource-intensive activity. I dare you to say to a field engineer to give me 1,000 rollouts of some robot field experiment. They might not like you as much right after. But additionally, when we do long-term predictions in simulation, we tend to make assumptions about the environment and the relationship the environment has to our agent, whereas in the real world, these things are very coupled and they change in time. Like, for example, if you have a walking robot walking in muddy ground, each step that the robot makes is going to leave an imprint on that ground, and the ground is going to change over time. And so we cannot expect this this connection to be modelable at least in a feasibly modelable for real-time use. And so we need to instead be willing to adapt incrementally and online. And I'm not going to be talking too much about this specific example. You can see my advisor's talk, Todd Murphy's tomorrow, for more on that. Finally, yet another seemingly obvious observation is that the capabilities of our agents are constrained by their body morphology and their actuators. No matter how much you ask a quadcopter to fly to the moon, it's not going to be able to do it. So the takeaway is that not all motion plans are physically feasible. And to use an obvious example here, if I were to put you in a car and ask you to parallel park, you probably wouldn't just magically slide your car into the parking spot quite like that. You probably do something more clever, requiring a string of actions over time that is non-trivial. And so basically this tells us that we are constrained by the controllability properties of our system. The issue with traditional learning methods in this sense is that we typically in reinforcement learning, for example, we drive our systems with random inputs and hope to explore the space of possible actions or system behaviors using random inputs. But in general, we can't quite rely on this because we're not guaranteed to generate coverage over all the possible robot behaviors by just driving it with random inputs. So this is something that is commonly known to control theorists, but it's less appreciated in machine learning. And it's the takeaway is that controllability is really important. And so taking all these things together, it's clear to us that physical learning is a structurally different problem from traditional machine learning, and that embodied learners are going to have unique needs that traditional learners don't. And so to this end, we have argued for the development of a field of robotic active learning. And specifically, we have this review paper coming out soon in iFact Mechatronics that we hope to check out on this exact subject matter. And instead, we propose that the robotic active learning pipeline be much more real-time, adaptive, and incremental. Here, we have the sort of basic flowchart of robotic active learning, where we're going to plan actions, where we hope to gain informative measurements. We're going to go collect those measurements and measure their informativeness, and then use them to update our learning representations or achieve our learning tasks. And then this new learned representation is going to reinform our plans and control actions so that we keep doing this loop, always adapting, always getting better. So now I'd like to discuss some results that highlight all of how one might deal with all these different issues that I've pointed out, all these differences between physical learning and traditional learning, in the context of several unpublished results that I've put together over the last year or so. And so to get us going, here's an example system. This is a brilliant video. This is from the Biomimetic Millisystems Lab at Berkeley. And this robot is an example of a spring-loaded inverted pendulum, or a slip model, as I'll be referring to it. And as you may expect, it's kind of a nightmare to control. It's non-linear, non-smooth, and it's intrinsically unstable because it's basically a pendulum, and we've gotten rid of its stable equilibrium point. And yet, besides all of these issues, it's one of the most popular models of human and animal locomotion, certainly on the basic end of things. And we're going to model it here as effectively a mass on a spring, and we're going to have it bounce around. And this is a 9-dimensional state-space model that obeys all these same properties, and it moves in 3D. Okay, so to get going, let's think about safety. In general, it's pretty difficult to know what is safe or what isn't when we don't know anything about our environment or our agent or our dynamics. And so really, to get going, we're going to have to assume something. So let's say that we have some area that we know is safe in some sense. Then, if our dynamics have bounded gradients, if we don't just blow up, we can use what are known as control barrier functions, or CBFs. And CBFs are Lyapunov function-like things that give guarantees that sets of initial conditions are forward invariant. So we're never going to really leave these set of states that were safe. And these guarantees can actually hold in pretty extreme cases. To demonstrate this, I'm going to be showing you trajectories generated by an algorithm that I've put together that basically takes dynamics and it makes them into stochastic processes. It makes them match the statistics of a given reference stochastic process. And specifically, we're going to be taking this slip model that I just showed you, and I'm going to be asking it to mimic Brownian motion over the plane, but subject to the constraint that we have to be safe and within the domain of this N, as is tradition to have your Northwestern or your university initials in some figure at some point in your PhD. And so, as you can see here, when we let the algorithm run, using control barrier functions, we can use the robot to explore the domain without leaving it or without falling, as you can see in the snapshot over time of the hopping trajectory. And you may say, great, that's cute. What about in more complex environments? And so here we have the same type of idea, but now over a floor plan. And as you might expect, it works great, even though we have all these different walls that we're now constrained by. The robot is capable of exploring nicely using this diffusive algorithm. And moreover, it extends easily to multi-agent settings, which is convenient. Okay. While control barrier functions are amazing, there are a lot of other ways to deal with safety. And so this is by no means meant to be representative of safe learning as a field. Great, so moving on now to our second difference, measurement models. We're going to stay with this example of the floor plan. So to state the obvious, robotic agents acquire information through their sensors, and their sensors are often myopic. And so we're going to need to use trajectories to figure things out. So still in this floor plan, our goal is going to be to learn the location of some object of interest subject to a local measurement model. And this kind of mimics the type of structure of a problem that you might see in search and rescue operations. And so Our slip robot is only aware of its immediate surroundings, which is to say it can only really measure right below where it's standing. And so using our algorithm where we mimic a diffusion process, the robot is going to be moving around, exploring everything until it gets within range of the signature of the object that we're interested in. So that's that quarter circle that you see there. And then once it gets in range, it'll be attracted to where the object is and succeed. So here you go. That's exactly what we might expect. There are a lot of other ways in which you might deal with local measurement models. Like, for example, animals have very complicated measurement models, such as, say, like sensing electromagnetic fields. And so something this simple might not be amenable. Sometimes you may need to actually learn these measurement models. And that's a whole other beautiful area of research. Okay, but keeping it moving along, let's go right back to controllability. Why are we talking about controllability? Well, in the reinforcement learning literature, as I was saying earlier, it is standard to drive systems with random actions in order to learn how to control them. And historically, this isn't a particularly mystifying thing. The reinforcement learning literature sort of split off from the multi-armed bandit learning setup. And the idea there is imagine that you are presented with 3 slot machines. You're a gambler and you're presented with 3 slot machines right in front of you. You're trying to maximize your payoff, and each machine may have a different expected reward that you're going to get from them. And so the idea, the learning problem, is that you got to figure out what's your best strategy to make the most money out of these different machines. So you're going to be pulling a lever and then observing a reward. And that's actually the key. That's the key difference. When it's based on the assumption that when you pull the lever, you get to see what happens. But that's not always the case in control systems, as I was showing you with the parallel parking example. And additionally, we don't expect it to work with systems such as Smarticles, which is this beautiful system near and dear to me. They're just 3 simple 3-linked robots with 2 servo motors on them, and you basically only set an angle to their flaps. As you can probably imagine, there are infinitely many useless combinations of angles that don't lead to any behavior that's remotely desirable. And so if we actually want to observe the full set of system behaviors, we're going to actually have to be carefully considering the relationship between our control system and the signal that we're inputting into it. And this is exactly the thing that we did in our recent science paper that came out this year with my collaborator Pavel Shivikov. He actually gave a talk on this paper at this conference on Monday, so feel free to check that out. And basically what we proved in this, this is more of a physics paper, in this thermodynamic, non-equilibrium thermodynamics paper, is that the emergent behaviors of complex systems are crucially dependent on their input response properties. And those input response properties can be quite non-trivial. So basically the energy that we pump into our system, here to be interpreted as our control signal, and its properties, they can couple in non-trivial ways to our system. And what's more, recently, we've been making provable connections between these ideas and the ideas of controllability. But to drive the point of this controllability point home, here's an example from a different paper that I collaborated on, published in Science Robotics, where we have our Smarticles uselessly flapping in the ring, and then suddenly we flash a light, and then when you flash a light, you cause a Smarticle to sort of like open up with arms like fully extended into a straight line, and then you make it inactive is what we call it. And so when it becomes inactive, the internal collision distribution of the ring all of a sudden becomes biased, and at this point, the system becomes controllable. And I don't mean this necessarily in a very formal sense. What I mean here is this is sort of existence proof, what you're seeing right here. Because we have a person literally herding the ring across a very simple maze. And what I'm going to be arguing is that discovering this behavior by simply taking random actions would have been extremely difficult. We can think of this in terms of the action distribution that we would have had to sample from. Basically, any noise distribution that you'd be considering, it would need to have some probability mass at 0, right? So that the angles can actually be flat, so that the Smarticle can be quote unquote inactive in some sense. But also you can't just do that, because then you might not get flapping motion, and the flapping is actually key. You need energy to be pumped into it so that like the collisions get this thing to move anywhere. And so what you start to notice is that we're going to be basically hand tuning and hand crafting this probability distribution in a really difficult and specific way. And my argument is that this is not something that would be easily achievable using something like reinforcement learning, at least naive reinforcement learning. And I back that claim up because I spent months trying to do this, and it was a nightmare. And so to actually get this thing to work, we had to bootstrap our physical understanding of the statistical mechanics of the behavior of the system, which captured the controllability into the model that we use for control. This is a simulation here where basically what we're doing is we're choosing which smarticles are inactive at any one moment in time, and this biases our collision distribution in a way that makes the system controllable. And this is great, but it was a Pyrrhic victory in a sense, in that it took a lot of effort to get to this point. And so I was asking myself, can this process be automated to improve learning? Great. And so coming back to the perspective that we put together during our development of rattling theory, I was able to derive a sort of controllability index, in a sense, from this theory of rattling that is actually amenable to learning tasks. Like you can put it into the learning objective of some problem, and it'll try to influence the behavior of the learner so that the controllability is kept in mind. Importantly, an important distinction here is that when you have a task that is just about like achieve this, right? Like when the learning is about policies, you're trying to learn a policy that solves a problem, we could be talking about the system controllability on its own. And that basically asks the policy to think about what is the system capable of as it's trying to learn the task. But if we have a more sort of like joint model system learning, where we perhaps don't know our system dynamics to begin with, then we can be talking about the controllability of the joint model system, which is to say, how do my actions influence the parameters of our model? So if we have, say, a neural network, which is a ton of parameters, and it's going to be learning the dynamics of our slip model yet again, how do the actions, the trajectories of my agent, induce changes in the evolution of the parameters of my neural network? And so this is what we try to achieve by adding this controllability index into our problems. And so to illustrate this approach and how it could be successful or useful, we tried to solve a simple model-based RL task using, again, the slip model as an example. So the goal is pretty simple, is to synthesize control to reach the desired position. So move from point A to point B, again, in 3 dimensions, and hopefully trying to keep in mind safety as well. But that can be really challenging if you don't know anything like your model. And precisely the point, we don't know anything about our model. All we're going to be given is an untrained neural network. And so we're going to also be doing this in one shot, so to speak. We're not doing this in real time because that's simply not doable with neural networks at this stage, but we can imagine a future where maybe that's maybe much more rosy. So let's see how this worked. Well, we found that our controllability aware model-based reinforcement learning algorithm converges faster and to a more accurate model. Not just that, we found that it achieves better task performance as well. And what we're comparing to here is the path integral formalism of model-based reinforcement learning that Evangelos Theodorou and his group have pioneered. And basically, we found that using their exact same, effectively the exact same problem structure, and then with just the added controllability index into the learning problem, that this actually accelerates learning by a fair amount, and it leads to better task performance. So in conclusion, what I want you to leave this talk with is the knowledge that physical learning is a distinct problem from conventional machine learning in a formal sense, and that embodied learners have many unique demands and requirements that we have to develop new methods and theory for. Moreover, we suggest that in order to make progress in this, we should actually think of this problem as its own substantive area of research, and we should study it in its own terms. And now I'd like to thank everyone that I worked with along the way to show you these results. And as well, these are all the references. Feel free to take a screenshot if you'd like that I used during my talk. And now I'd like to open the floor for questions.
Okay, thank you very much, Thomas. As Thomas just said, we have some time for questions. So if you